Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Environmental Degradation of Materials Corrosion Part 1 from the paper Functional Materials. The purpose of this module is to make the students familiar with first the fundamentals of corrosion and the electrochemical nature of corrosion, second the thermodynamics and kinetics of corrosion. So students, let us start with the basic introduction about the module. Metals and alloy constitute the most significant group among all the engineering materials because of their specific properties, like the combination of strength and ductility, very high thermal and electrical conductivities, excellent malleability and formability, magnetic properties, etc. The most common property among all is the ease of forming into a desired shape for the majority of engineering applications. Even though the metallic materials have high use, they have one major drawback. Their interaction with the environment during the use can influence the properties adversely, which is leading to premature and, in many instances, sudden failure. Many cases, these could cause plant shutdown, loss of economy, and risk to human life, environmental pollution, and other allied damages. Therefore, materials degradation can be defined as the loss of performances and efficiency of engineering components. Loss of performances could be of any form, ranging from loss of strength, loss of reflectivity, loss of conductivity, or even the loss of appearance or aesthetics of the component. The interaction between the metallic materials and the environment depends on various factors like composition and the microstructure of a metal, processing, size, shapes, and design of the component, nature of the environment, that is aqueous, dry, radiation, etc., nature and duration of interaction, temperature, pressure, and many other factors. Material degradation thus can be classified into various categories. Amongst all, the corrosion is the most experienced reason for the material's failure due to environmental interaction of metallic materials with the environment. Apart from environmental degradation, there could be mechanical causes for the failure. For example, accidental increase of the load on an engineering component could lead to fracture. Wear of the meeting surfaces could also loosen the tightly fixed component, like failure of axle. Even the heat energy or electromagnetic radiation can also have massive damaging effect. However, here we will be discussing only the corrosion and the part 2 will discuss the fundamentals of oxidation. Material degradation. Mechanisms of material degradation and the characteristics of the economically significant forms of damage to the materials are discussed in terms of the physical and chemical processes involved. There is a wide range of materials degradation mechanism, but all can be classified into four basic categories. First, by direct mechanical action, second, by heat or radiation, and third, by the presence of chemical reagents. So students, these are the figures showing the effect of corrosion in various fields. That is, as you can see over here, these are the figures. First figure corresponds to life safety. Second, the corrosion in the regulatory compliance. The next in the economics, and the last figure is in the environmental. And the left hand side figure shows the radiograph corrosion of screws in retained surgical plate placed 40 years earlier for femur fracture and fuzzy debris around the screws. Now let us discuss the definition of material degradation. Material degradation can be defined in terms of loss of performance of an engineering system. Loss of performance can be related to many parameters such as first, the loss of reflectivity in optical equipment due to fungal attack. Second, the loss of mechanical strength of a structural component exposed to a corrosive medium. Third, wear can increase the clearance between the piston ring and cylinders, hence incomplete combustion of the compressed gas. Next, the loss of efficiency, loss of lifetime, extensive control component, and the routine. Almost any known natural phenomenon can cause material degradation, such as heat, light, short wavelength, electromagnetic radiation, radioactive emission, chemical, mechanical stress, and interaction with bacteria, fungi, or other life forms. Classification of materials degradation according to its basic cause is a first step in any plan to protect a specific material in a specific situation. Now students, let us discuss the definition of corrosion. The practical definition of corrosion is that the tendency of a metal to revert to its native state, whereas the scientific definition is the electrochemical degradation of metal as a result of a reaction with its environment. So continuing our discussion over the definition of corrosion, the destructive attack of a metal by chemical or electrochemical reaction with its environment. Corrosion returns the metal to its oxidized state or combined state in chemical compounds that are similar or even identical to the minerals from which the metals are extracted. So, considering the aqueous corrosion, that is Zn plus 2HCl gives ZnCl2 plus H2, 2Al plus 3H2O gives Al2O3 plus 6H plus, whereas in the oxidation we have 2Fe plus 3O2 gives Fe2O3. In high temperature corrosion, Fe plus CO2 gas gives FeO plus CO, and the rusting corresponds to 2Fe plus H2O plus O2 gives 2FeOH2, whereas 2FeOH2 plus H2O plus O2 gives 2FeOH3. So corrosion resistance be affected by metallurgical, electrochemical rate, mechanical, and thermodynamics factors. Now let us discuss the electrochemical nature of corrosion. Consider when a zinc metal or a zinc rod is immersed in hydrochloric acid. Visibly, hydrogen gas bubbles forms on the surface of zinc rod, and then there forms on the surface of zinc rod, and then gradually zinc loses its mass in the form of zinc ions in the solution. That is, the reaction rate can be written as Zn plus HCl gives ZnCl2 plus H2. If the above reaction is written in the form of half cell reaction, two different reactions occur in order to maintain the electrical neutrality. One is the cathodic reaction, where electron is accepted by the hydrogen ion present in the acid solution. Other reaction is the anodic reaction, where electron is generated from the zinc atoms for the supply of electron required for the cathodic reaction. This is needed to maintain the charge balance. Hence, two half-cell reactions can be written as Zn minus 2 electrons gives Zn2 plus, that is the anodic reaction. 2H plus 2 electrons gives H2, corresponds to the cathodic reaction. Interestingly, both reactions are taking place on the zinc rod. Hence, zinc is acting as both the cathode or the anode. In addition, for the flow of hydrogen ions from the solution to the surface of the zinc rod, as well as this solution of zinc ions generated at the metal solution interface requires an electrolyte. Moreover, the electron liberated due to the dissolution of zinc ion at the metal surface migrates through the metal electrode to the site where hydrogen ion gets reduced. All the four processes are clearly depicted in this figure. Hence, loss of weight of zinc rod or corrosion of zinc happens due to the electrochemical nature of the above process. It is true in the case of any corrosion reaction. There could be possibility of multiple cathodic or anodic reactions at one place. However, overall charge balance will always be maintained. During metallic corrosion, the rate of oxidation equals the rate of reduction. Any electrochemical reaction which can be divided into two or more partial reactions of oxidation and reduction, it is termed as redox reaction. So the important basic principles of corrosion can be presented in the following more points. The law of conservation of mass applies to chemical and electrochemical reactions, that is, matter cannot be destroyed only changed from one form to another. Second, the reaction can be the gain of electrons or reduction reaction, or it can be the loss of electrons, oxidation reaction, and the total charge must be the same as that of before and after the electrochemical reaction. If anywhere in a material electron acceptance reaction takes place, there must be an electron loss reaction. The metals loses electrons and enter into the environment in the ionic forms. All the corrosion reactions, that is material loss by electrochemical reactions, are oxidation reactions. Lastly, in the case of aqueous corrosion, the ions enter the corrosion product or into the solution electrolyte. So, from the discussion which we have done till now, there are the electrochemical cell consists of the following: the electrode, that is the interface between a metal and a solution across which the charge transfer results from an electrochemical reaction. Next is anode, the electrode on which the anodic oxidation reaction occurs. The cathode, the electrode on which a cathodic reduction reaction occurs. And lastly, the electrolyte, an ionic conductor. So students, let us now discuss the basic parts of corrosion cell. First, the anode, a metal electrode in contact with the electrolyte which corrodes. Second, the cathode, a metal electrode in contact with the electrolyte which is protected against the corrosion. Third, the electrolyte, a solution or conducting medium such as soil, water, or concrete which contains oxygen and dissolved chemicals. Lastly, we have a metal path, an external circuit that connects the anode and the cathode. So this shows the different forms of corrosion. The factors affecting the forms of corrosion are the microstructure, environment, stress, geometry, and the time. So as you can see from the first figure, we have the hydrogen damage. So we have a uniform surface, and as you can see on the right hand side of the figure, there is a formation of internal voids and surface cracks. The next figure, we have the galvanic, where we have the intergranular. And the third figure shows the crevice, and on the right hand side of the figure, there are de-alloying. Now, on the right hand side, we have the different environmentally induced cracking, and in the below figures, we have stress corrosion, corrosion fatigue, and hydrogen induced cracking. For any spontaneous process, overall Gibbs free energy, that is G, must decrease. Negative value of delta G indicates the spontaneous possibility of the reaction, whereas its positive value definitely indicates that the process is non-spontaneous. When the change in free energy is zero, it suggests equilibrium. Free energy change for any electrochemical reaction is calculated from the following equation, that is delta G is equal to minus N multiplied by F multiplied by E, where delta G is the free energy change in joules, N, F and E are the number of electrons involved in the reaction, Faraday's constant, and cell potential in volts respectively. If standard state is maintained, then the above equation can be written as delta G degree is equal to minus N F E degree. The right-hand side of these two equations contains the negative sign. Positive potential ensures a negative change in free energy or spontaneous reaction. So, if a metal electrode is immersed in an electrolyte, electric double layer develops. These double layers are called as inner and outer Helmholtz planes. This is similar like a charged capacitor. Salvation of ions by polar water molecules is shown in this figure. Electric double layers develops a potential difference at the electrode-electrolyte interface. This is called as electrode potential. Now, a complete electrochemical cell consists of two half-cell reactions. Hence, with reference to the formation of the single metal electrode system in equilibrium with the same metal ions in the electrolyte. So, the reaction is written as M to the power plus N plus Ne gives us the M. However, in an electrochemical cell, both the cathode and the anode there develops potential at each electrode, and the final cell potential is the algebraic difference of both the electrode potentials. So, this figure 4 shows the creation of electric double layers once a metal is immersed in an electrolyte. With reference to the Daniell cell, the copper and the zinc electrode would also have the same electrode potential. Then the electrode potential at both the electrodes can be expressed with the help of Nernst equation. Kinetics of corrosion. The kinetics of corrosion, or we can say that the thermodynamics of electrochemical reactions predicts the possibility of a cell reaction. However, until we talk about the kinetics of the process, it remains the incomplete study. The kinetics of electrochemical dissolution depends mainly on Faraday's law of electrochemistry. The amount of dissolution of a metal can be found out from the following formula, that is, W is equal to I multiplied by T multiplied by A divided by N multiplied by F, where W is the mass loss, I, T, A, N and F are currents in amperes, time duration of the exposure, atomic weight of the dissolving metal, number of electrons, and Faraday's constant respectively. Therefore, the rate of dissolution can be determined by dividing W with time and surface area of the metal exposed to the electrolyte. Therefore, R is equal to W by T multiplied by A, which is equal to I T A divided by N F T capital A, which is equal to I small a divided by N F, where small I is the current density. When the reduction and the oxidation reaction rates with reference to single electrode reactions, example M to the power plus N plus Ne gives us M, at equilibrium conditions are equal, there will not be any net loss of metal in the form of ions or net deposition of metals. At this time, current density can be considered as the exchange current density. Exchange current density is a vital kinetic parameter for deciding the relative corrosion rates of many metals and alloys. Laws of electrolysis. First, the amount of chemical change which occurs at any electrode is strictly proportional to the quantity of electricity passed through the electrolyte. Second, if the same quantity of electricity is passed through different electrolytes, the different amounts of chemical changes produced are all chemically equivalent. So, continuing the discussion on the kinetics of corrosion, interpreting the rate of an electrode reaction is often more complex than understanding a homogeneous reaction because an electrode process is a heterogeneous reaction occurring only at the electrode-electrolyte interface, with a rate that depends on the mass transfer to the electrode and various surface effects in addition to the usual kinetic variables. Since electrode reactions are heterogeneous, their reaction rates are usually described in the units of mole per second per unit area. So the relation between the flux of ions flowing out of the surface, that is the corrosion reaction, and the current density using the following relation, that is M is equal to I multiplied by T multiplied by A divided by NF. I is the current, T is the time, N number of electrons, and A is the area of cross section. So I multiplied by T is equal to the total current. I multiplied by T divided by NF is equal to N moles electrolyzed. ITA divided by NF is equal to total mass. So rate is equal to dm by dt. So M multiplied by T capital A equal to IA by NF. The above expression shows that the rate of corrosion is related to the current density. This can be expressed in terms of the units of penetration per unit time by dividing by rho. So M divided by TA rho is equal to IA by NF rho. So M divided by T multiplied by A multiplied by M by AL is equal to ML by TM is equal to L by T. That is the unit penetration per unit area. More than one anodic reaction and more than one cathodic reaction, I current is equal to summation over IA is equal to minus summation over IC. IA corresponds to the anodic reaction and IC corresponds to the cathodic reaction. So students, let us summarize what we have learned in this module. First, the material degradation along with its basic types and material degradation due to natural phenomena are all discussed. Second, the fundamentals of corrosion, including its definition, electrochemical nature of corrosion, and its different forms are discussed. Thermodynamic and kinetic analysis of corrosion are also explained in detail. Thank you.